1. An organization wants to deploy a CMP solution in a private cloud. What requirements influence the sizing of the underlying cloud management infrastructure? A. Size of the service portal and catalog. B. CMP version and functions it provides. C. Type of services and cost of each service. D. High availability and performance. The correct answer is B. CMP version and functions it provides. Here's the explanation. When sizing the underlying cloud management infrastructure for deploying a CMP, cloud management platform, solution in a private cloud, the version and functions provided by the CMP are crucial factors. Different CMP versions offer varying levels of functionality and capabilities. The organization needs to ensure that the selected CMP version can support its desired features, such as automation, orchestration, resource management, and monitoring. Options A, C, and D are important considerations in the overall cloud infrastructure design but are not specifically related to the sizing of the underlying cloud management infrastructure. The size of the service portal and catalog, option A, may impact user experience but doesn't directly influence the sizing of the cloud management infrastructure. Similarly, the type of services and their costs, option C, and requirements for high availability and performance, option D, are significant but are not directly related to the sizing of the cloud management infrastructure. 2. A cloud architect is designing a hybrid cloud for an organization. A requirement for this environment is for federated access to both cloud provisioning APIs. What must be configured between both cloud providers' authentication mechanisms? A. Shared super user account. B. Trust relationship. C. Identical accounts. D. IPsec VPN. The correct answer is B. Trust relationship. Explanation. In a hybrid cloud environment where federated access to both cloud provisioning APIs is required, establishing a trust relationship between the authentication mechanisms of both cloud providers is essential. This trust relationship allows for seamless authentication and authorization across both environments, ensuring that users and applications can access resources and services in a secure and integrated manner. Option A, a shared superuser account, may introduce security risks and lacks the granularity of access control that a trust relationship provides. Option C, identical accounts, might not be feasible or practical, especially if the two cloud providers have different authentication systems or policies. Option D, IPsec VPN, is used for secure communication between networks but is not specifically related to federated access to cloud provisioning APIs. While it can provide secure connectivity between on-premises and cloud environments, it doesn't directly address the authentication mechanisms between the cloud providers. 3. When considering a packaged PaaS solution, what is a potential advantage? A. Greater control over infrastructure management. B. Lower cost of ownership. C. Longer time to market for applications. D. Reduced reliance on third-party vendors. The potential advantage of a packaged PaaS, platform as a service, solution is B. Lower cost of ownership. Explanation. Packaged PaaS solutions often come with streamlined infrastructure management, which can lead to reduced operational costs compared to managing infrastructure on premises or through other cloud service models. PaaS solutions typically abstract away much of the underlying infrastructure complexity, allowing organizations to focus more on application development and less on managing hardware and software infrastructure. Option A, greater control over infrastructure management, is not typically associated with packaged PaaS solutions, as they abstract away much of the underlying infrastructure to provide a simplified development experience. Option C, longer time to market for applications, is not a typical advantage of PaaS solutions. In fact, PaaS solutions often accelerate time to market by providing pre-configured development environments and services. Option D, reduced reliance on third-party vendors, is not necessarily true for PaaS solutions, as they often rely on third-party vendors for underlying infrastructure and services. However, they can reduce the complexity of managing multiple third-party vendors for infrastructure components. 4. What is a primary driver for organizations to adopt cloud solutions in the context of digital business imperatives? A. Reducing compliance requirements. B. Simplifying on-premises infrastructure. C. Accelerating innovation and agility. D. Increasing hardware procurement costs. The primary driver for organizations to adopt cloud solutions in the context of digital business imperatives is C. Accelerating innovation and agility. Explanation. Cloud solutions provide organizations with the flexibility and scalability needed to rapidly innovate and adapt to changing market conditions. By leveraging cloud services, organizations can quickly deploy new applications, experiment with emerging technologies, and scale resources as needed, allowing them to stay ahead of competitors and meet evolving customer demands. Option A, reducing compliance requirements, can be a benefit of cloud adoption, but it's not the primary driver. Compliance considerations may influence the choice of cloud provider and deployment model, but they typically aren't the main reason for adopting cloud solutions. Option B, simplifying on-premises infrastructure, is another potential benefit of cloud adoption, but it's not the primary driver. While moving to the cloud can reduce the burden of managing on-premises hardware and software, the primary motivation is usually to gain agility and innovation rather than simply reducing complexity. Option D, increasing hardware procurement costs, may be a factor that organizations consider when evaluating the cost benefits of cloud solutions, but it's not typically the primary driver for adopting cloud in the context of digital business imperatives. 5. A cloud architect discovers that an organization wants to deploy 500 consumer applications initially and grow to over 2,000 consumer applications in 3 years. These applications will use block storage only. How does the information impact the cloud management platform infrastructure sizing? A. Influences proxy server data storage requirements. B. Influences CDN data storage requirements. C. Influences federation server data storage requirements. D. Influences monitoring server storage requirements. The information provided indicates that the organization plans to deploy a large number of consumer applications that will primarily use block storage. This information impacts the Cloud Management Platform (CMP) infrastructure sizing in the following way. A. Influences proxy server data storage requirements. Explanation. When deploying a large number of consumer applications that primarily use block storage, the Cloud Management Platform (CMP) will likely need to handle significant amounts of data traffic related to these applications. Proxy servers are commonly used in cloud environments to manage and optimize data traffic, including requests to and from storage resources. Therefore, the increase in the number of consumer applications and their reliance on block storage will impact the data storage requirements of proxy servers within the CMP infrastructure. Options B, C, and D are less likely to be directly impacted by the deployment of consumer applications using block storage. Option B, CDN, Content Delivery Network, data storage requirements, typically involve caching and delivering content to users efficiently, which may not be directly affected by the use of block storage for consumer applications. Option C, Federation Server Data Storage requirements, usually pertain to managing identity and access across multiple systems, which may not be directly influenced by the number of consumer applications or their use of block storage. Option D, Monitoring Server Storage requirements, might be influenced by the increased workload and data generated by the growing number of consumer applications, but it's less directly tied to the specific use of block storage. 6. You are designing the CMP structure. Where should you define the pods? A. Fault domain. B. Private cloud VM. C. Availability zone. D. Public cloud VM. In designing the structure of a CMP, Cloud Management Platform, pods are typically defined within C. Availability zone. Explanation. Availability zones are distinct locations within a region, usually separate data centers, that are isolated from each other in terms of power, cooling, and networking. Defining pods within availability zones allows for redundancy and fault tolerance. By distributing pods across availability zones, the CMP can ensure high availability and resilience to failures within a specific zone. This architecture enhances the reliability of the overall system and helps maintain service availability in the event of failures or disruptions in one availability zone. Options A, B, and D are less common locations for defining pods in the context of a CMP. Option A, fault domain, typically refers to a grouping of hardware and infrastructure components that share a common point of failure. While fault domains are important considerations for resilience, defining pods within availability zones provides a higher level of fault tolerance. Option B, private cloud VM, is more related to the deployment of virtual machines within a private cloud environment and is not typically where pods are defined in a CMP architecture. Option D, public cloud VM, similarly refers to the deployment of virtual machines within a public cloud environment and is not where pods are typically defined in a CMP architecture. 7. An architect is designing the compute resource pools for a cloud. As part of the deliverables, the architect has included the standard specifications for the physical servers to be used. The organization has provided estimates for future growth but has concerns about whether these estimates are accurate. What should be included in the design to address these concerns? A monitoring application and procedures for pool expansion. B. A chargeback application and orchestration workflows to auto-scale pools. C. A metering application and orchestration workflows to auto-scale pools. D. A configuration management application and procedures for pool expansion. To address concerns about the accuracy of future growth estimates for compute resource pools in a cloud environment, the design should include A monitoring application and procedures for pool expansion. Explanation. 1. Monitoring application. Implementing a robust monitoring application allows the organization to track the actual resource usage and performance metrics of the compute resource pools in real time. This data can provide insights into actual usage patterns and trends, helping to validate or adjust the initial growth estimates. 2. Procedures for pool expansion. Having procedures in place for dynamically expanding resource pools based on observed usage patterns and actual demand ensures that the cloud infrastructure can adapt to changing needs over time. These procedures may involve automated or manual processes for scaling up resources as needed to accommodate increased demand. Options B, C, and D include elements that may be valuable in a cloud environment but are not specifically targeted at addressing concerns about the accuracy of future growth estimates. Option B suggests a chargeback application and orchestration workflows for auto-scaling pools, which focus more on cost allocation and resource optimization rather than validating growth estimates. Option C proposes a metering application and orchestration workflows for auto-scaling pools, which are related to tracking resource usage and adjusting capacity but may not directly address concerns about growth estimate accuracy. Option D mentions a configuration management application and procedures for pool expansion, which are important for managing infrastructure configurations but may not specifically address concerns about the accuracy of growth estimates. 8. When designing a cloud-in-a-box infrastructure, what is a key objective? A. Expanding the physical data center. B. Isolating compute and storage resources. C. Providing a scalable cloud-like environment within a single appliance. D. Reducing reliance on virtualization technologies. The key objective when designing a cloud-in-a-box infrastructure is C. Providing a scalable cloud-like environment within a single appliance. Explanation. A cloud-in-a-box infrastructure aims to deliver the benefits of cloud computing, such as scalability, flexibility, and self-service capabilities, within a single appliance or hardware platform. This solution typically includes integrated compute, storage, and networking resources, along with management software, to create a self-contained cloud environment. The primary goal is to provide organizations with a simplified and scalable infrastructure solution that mimics the characteristics of a public or private cloud without the need for extensive hardware procurement, deployment, and management efforts. Options A, B, and D are not the key objectives of a cloud-in-a-box infrastructure. Option A, expanding the physical data center, is a general objective related to data center growth and expansion but not specifically tied to the concept of a cloud in a box. Option B, isolating compute and storage resources, is an important consideration in cloud infrastructure design but is not the primary objective of a cloud in a box solution, which aims to integrate resources within a single appliance. Option D, reducing reliance on virtualization technologies, may be a consideration in certain cases, but it's not the primary objective of a cloud in a box infrastructure, which typically leverages virtualization technologies to deliver cloud-like capabilities. 9. An organization wants to deploy applications that can programmatically alter network behavior. In addition, they want to deploy additional network services in real time. Which cloud management component should be included in the design to support this requirement? A. Hypervisor Element Manager. B. Software-defined network controller. C. Network Management Controller. D. Virtual Switch Manager. The cloud management component that should be included in the design to support the requirement of deploying applications that can programmatically alter network behavior and deploy additional network services in real time is B. Software-defined network controller. Explanation. A software-defined network (SDN) controller is a critical component for managing and controlling network behavior in a programmable and dynamic manner. It enables centralized management and programmability of network infrastructure, allowing applications to dynamically adjust network configurations and policies based on their requirements. With an SDN controller, organizations can deploy additional network services in real time and automate network provisioning and management tasks. Options A, C, and D are not specifically designed to address the dynamic and programmable network behavior requirements described. Option A, Hypervisor Element Manager, typically focuses on managing virtualization infrastructure at the hypervisor level and does not directly address network behavior programmability. Option C, Network Management Controller, may provide network management capabilities but may lack the programmability and dynamic control features offered by an SDN controller. Option D, Virtual Switch Manager, is responsible for managing virtual switches within a virtualized environment but does not provide the level of control and programmability needed to alter network behavior programmatically in real time. 10. An organization plans to deploy many cloud-native applications that will generate a considerable amount of east-west traffic. The cloud-native applications will be deployed on hosts running hypervisors. Why would distributed routers be considered in this design? A. Enable network segment. B. Improve network performance between hosts. C. Minimize internet traffic. D. Protect against a physical router failure. The reason why distributed routers might be considered in the design for deploying many cloud-native applications generating considerable east-west traffic on hosts running hypervisors is B. Improve network performance between hosts. Explanation. Distributed routers, also known as distributed virtual routers, are virtual routing devices that are distributed across multiple hypervisor hosts within a virtualized environment. By distributing routing functionality closer to the virtualized workloads, distributed routers can improve network performance between hosts. Especially for east-west traffic, traffic between virtual machines or containers hosted on different hosts within the same data center. This distributed approach reduces the need for traffic to traverse physical network infrastructure, thereby reducing latency and improving throughput. Options A, C, and D are not directly related to the primary purpose of distributed routers in this scenario. Option A, enabling network segmentation, can be achieved through various network virtualization techniques such as VLANs, VXLANs, or overlay networks, and is not the primary purpose of distributed routers. Option C, minimizing internet traffic, may not be directly impacted by the use of distributed routers within a data center environment, as they primarily handle east-west traffic between hosts rather than traffic to external networks. Option D, protecting against a physical router failure, is a valid consideration for high availability but may not be the primary reason for deploying distributed routers. Distributed routers primarily aim to improve network performance and reduce east-west traffic latency within the virtualized environment.